Okay, so this video is going to be the solution video for the exam that I took in 2006. So let's jump right on into it. So the first question says an object moves along the x-axis so that its position is given by x of t is equal to k1t to the fifth plus k2t squared plus c1t plus c2. Here k1 and k2 are known constants and c1 and c2 are unknown. The velocity of the object is measured at the known time t is equal to t sub a and found to have a value of w. The position is measured at t is equal to 0 and is found to have a value of d. Determine c1 and c2 and the object's acceleration. Okay, so I'm going to do this one right off to the side of this problem. I should have enough room here. So let's just start by writing down the position function. So this is x of t is equal to k1 times t to the fifth plus k2 t squared plus c1t plus c2. I'm not the biggest fan of that c1, so let's go ahead and write that a little bit bigger. So this is c1t. Okay. Now, we're told something about the initial position. And to remind you, we don't know what c1 is, and we don't know what c2 is. But because we're told something about the initial condition, we can solve for c2 right away. And that's because we know x of t is equal to 0 is equal to d, which is equal to k1 0 to the fifth, 0 to the fifth plus k2 0 squared plus c1 times 0 plus c2. So this says that c2 is equal to d. Okay. Now, the next thing we can do is we can determine what the velocity as a function of time is, because we know the relationship between the velocity and the position as a function of time is given by v of t is equal to dx dt, which is equal to d by dt of k1 t to the fifth plus k2 t squared plus c1 t plus c2. And so all we need to do is apply our derivative formula for powers, and that's to say that the derivative with respect to time of t to the n is going to be equal to t to the n minus 1 times n. And we also know that the derivative of the sum is equal to the sum of the derivatives, and so that means that what we're going to do is we're going to apply this derivative term by term. Okay, so we're going to first apply it to the first term, so this is going to tell us that this is going to be equal to 5k1 t to the fourth plus 2k2t plus c1. And then the last term, because c2 is a constant, the derivative is just 0. Okay, so this is our velocity as a function of time. And then what we know is that we have some condition for t is equal to ta. So when t is equal to ta, we know that the velocity t is equal to t sub a is going to be equal to w. So this is going to be equal to w. And then we just take our velocity function and evaluate it at ta. 5k1 ta to the fourth plus 2k2 ta plus c1. Now, everything in here is now a known constant because ta it's a value of time. It's like saying it's been like 10 seconds or 5 seconds. And k1, k2, and w are also all known. The only thing that we don't know here is c1. And so what we can do is we can solve for c1 by algebraically moving everything to the other side. And so that says that c1 is going to be equal to w minus 5k1 ta to the fourth minus 2k2 ta. And let's put boxes around all the things that we've found so far. So this is, we have c2, we have c1, and the last thing that we're asked to find is what the acceleration is. And so in order to find the acceleration, what we do is we say that the acceleration as a function of time is going to be equal to the derivative with respect to time of the velocity And so this is going to say that this is d by dt of, we can take our velocity function and plug it in down here. So this is going to be 5 k1 t to the fourth plus 2 k2 times t. Take our derivative with respect to time, term by term. This says that this is going to be equal to 20 k1 t cubed plus 2 k2. Okay, and that's our acceleration as a function of time. Okay, so that's the first question. The second question says that a rocket travels along a straight vertical line, starting at time defined to be t is equal to 0, at a point defined to be the origin. Its velocity, its vertical velocity is observed to be v of t is equal to minus k1 t squared plus k2 times t, where k1 and k2 are known positive constants. What is the rocket's maximum height? Okay, so let's go ahead and get started with this one. So this one, we're given this velocity as a function of time is going to be equal to minus k1 t squared plus k2 times t. Now, we want to find what the maximum height is. And so we know that when something reaches a maximum height, or when something turns around, that means that its velocity is equal to 0. Or by, in a similar way, the position is not changing. So if the position is not changing, we say that the rate of change of the position with respect to time is equal to 0, which is the same thing as saying the velocity is equal to 0. And I'm going to be very explicit. I'm going to say that this is going to be t when t is equal to t max, so the time it takes to get to the maximum height. So the velocity at the time it takes to get to the maximum height is going to be equal to minus k1 t max squared plus k2 t max. And remember that this is going to be equal to 0. In order to find when the velocity is equal to 0, we can factor out a t. So then we're going to have a t max times minus k1 t max plus k2 is equal to 0. And there are two solutions to this. One is what's kind of sometimes called the trivial solution, and then the other is the one that we're really interested in. This is satisfied when t max is equal to 0, or like when we begin. It starts with 0 velocity. But that's not particularly interesting. What we really want here is when the time t max here satisfies this portion of the equation, right? So when we satisfy this portion, we can say that t max is going to be equal to k2 over k1. Okay, so that's when this is going to satisfy this equation, and this is the time that it takes to have a velocity of 0. Okay, so now we know how long it takes to get a velocity of 0. We need to evaluate that in our position equation in order to determine what the maximum height actually is. But before we can do that, what we need to do is we need to determine what the position equation actually is. And so in order to do that, we can say that the time rate of change of position, here I'm calling it y because we're talking about something that goes vertically, okay? So dy dt is going to be equal to v of t. And so I can multiply both sides by dt, and we can integrate this. And so this tells me that y of t is going to be equal to the integral of v of t dt, which is going to be the integral minus k1 t squared plus k2 times t. Let's put some parentheses and a dt. And now the integral of the sum is equal to the sum of the integrals, so we can just do this integral term by term. And so we see then, using our rule for integrals of powers, t to the n dt is equal to t to the n plus 1 over n plus 1 plus some constant integration. Okay, so let's apply that right here. It says this is going to be equal to minus k1 t cubed over 3 plus k2 t squared divided by 2 plus a constant integration. So this is our y of t. Now we need to evaluate what this constant of integration is going to be, and there is some information in the statement of the problem that's going to help us. And that is to say that in the statement of the problem it says, at a point defined to be the origin at time t is equal to 0. So what that says is that y of t is equal to 0. So when we evaluate our function when the time is 0, the height is 0. And so ultimately what this says, we can be very explicit here and really evaluate our function with t is equal to 0 divided by 2 plus c. This says that c is equal to 0. So at the end of the day, our position function y of t is going to be equal to minus k1 t cubed over 3 plus k2 t squared over 2. And now that we have our position function, all we need to do is take the time it takes to get to the maximum height and evaluate our position function. And this is just to say that y max, the maximum height it gets to, the maximum distance it goes in the y direction, is going to be equal to y of t is equal to t max, which is equal to minus k1 times, I need to remember what this was. This was k2 over k1. So, so this is evaluated t max, but really just to make this really explicit, y of t is equal to t max is going to be equal to y of t is equal to k2 over k1, right? Because that's what t max is, right? We said t max is k2 over k1, and so let's evaluate this function with this. So this is going to be minus k1, k2 over k1 cubed divided by 3 plus k2 times k2 over k1 squared divided by 2. We could simplify this a little bit further if we want. So then we said this was going to be 1/3. We can cancel a k1 here and here, so this is going to be k2 cubed divided by k1 squared plus, this is going to be plus k2 squared, so this is k2 cubed divided by k1 squared with a half here. Okay, so now we can kind of look at this in terms of dimensional analysis. Sorry, I lost a factor to my subscript of 2 here. We can look at this in terms of dimensional analysis, and what we see here is that these two terms can add together, right? And they should be able to add together because the units need to be the same, okay? So I can add these two together if I find a common denominator, and so that makes this a 2 over 2. This makes this a 3 over 3. So this is going to tell me ultimately that I have 5 over 6 k2 cubed divided by k1 squared. And this is what y max is going to be equal to. Okay. Now, for our purposes, and for you, if you were doing a problem like this on the exam, you don't necessarily have to reduce it this far. But part of the reason why it's worth doing it like this is because, for one, I can check my dimensional analysis, and I'll do that in just a second. For another, if I did have some values for this, like some numerical values for this, what I would want to do is I'd want to express this in the simplest way possible and then plug my numbers into it. Because if you start plugging numbers in earlier on, then you're going to have to use your calculator multiple times in order to get to your final answer. And not only does that take longer, but it also gives you more opportunities to make mistakes if you're plugging something into a calculator, okay? So we want to try to express our answers in the simplest way possible. Like I said, that's not something I'm going to grade you on. That's not something I require you to do. But if you start getting good at doing that, everything's going to be a lot easier for you as you're moving into your upper level classes. Okay, so like I said, I promised we're going to check our dimensional analysis. And in order to do that, let's go back to our original equation that we had here. So we had our velocity as a function of time is equal to k1t squared plus k2 times t. So we know the left side is going to have units of meters per second. So that says that meters per second has to be the units of k1t squared. And so this says that k1 has units of meters per second cubed. And likewise, for k2 has units of meters per second. So meters per second are the units of k2 times t. Sorry, k2 times t is meters per second. And so this tells me that k2 has units of meters per second squared. Okay, so there's our dimensional analysis, but let's see if that holds for our answer at the bottom, because what we have here, we have k2 cubed divided by k1 squared. So if we have k2 had units of meters per second squared. Sorry, this is k2 had units of meters per second squared, and so we had I think it wasn't meters per second squared? I'm already forgetting. Meters per second squared and meters per second cubed. Okay, so k2 had units of meters per second squared. k1 had units of meters per second cubed. And what we want are, what are the units of k2 over k1, where k2 is cubed and k1 is squared. Okay, so let's take a look at this. So this is going to tell me that I have units of meters per second squared cubed divided by units of meters per second cubed squared. Okay, so when I do this, what I'm going to have ultimately is this is going to be meters cubed per seconds to the 6 divided by meters squared per seconds to the 6. We can cancel our seconds to the 6. We can cancel 2 factors of meters, and what we're left with is that this has units of meters. And that's exactly what we need, because we're solving for a height. We're solving for something that has units of meters. Okay? So that's a nice way that we can use our dimensional analysis to check our answers. Okay. Our last question is the most complicated out of the 3, and that's because this is a 2-dimensional motion problem. And we've gotten quite a bit of practice with these, and as we're doing them, we're really seeing that all of these problems are kind of the same when it comes to 1-dimensional motion, 2-dimensional motion. We have to know, how do we go from position to velocity to acceleration, from acceleration to velocity to position. And then, if we do that in 1 dimension, how can we extend that into 2 dimensions? Okay. So when we want to look at this problem, this one says a robot has been programmed so that it has an acceleration given by a vector is equal to 0 I vector, or I hat, minus beta times t times j hat in the coordinate system below. Here, beta is a known constant. The robot is placed at point x is equal to 0 and y is equal to a at time t is equal to 0. And is given some velocity, some initial velocity, v1 vector, so that it can pick up some object at a point c. X is equal to c, y is equal to d. Here, a, c, and d are known. What is the position? What is the robot's position as a function of time? Okay. So as I've done these kinds of problems, what we see is there's kind of 2 ways to approach it. And one way is to do this in terms of a table where we can break this into our x equations and our y equations. Or, alternatively, you can do this in full vector notation. Vector notation. Okay. Now, I'm going to opt for doing this problem in the vector notation. So I'm going to get rid of what I just put here, and we're going to grab you. We're going to move you over here, because it's already written in terms of vector notation. So why not use it the way that it's written? Okay. So we have our acceleration as a function of time in general is going to be equal to 0 times I hat plus, this is going to be minus, so this is going to be minus beta t times j hat, okay? And we want to find the position vector, but in order to do that, we're going to first have to find the velocity vector. And so we know that the acceleration as a function of time is going to be equal to dv dt. We want to get v, so we multiply both sides by dt, and then we integrate. So this says that v of t vector is going to be equal to the integral of 0 I hat minus beta t j hat times dt. Okay. Now here, I'm going to be very explicit with the way that I'm breaking this apart, because when you do this, this integration in vector notation, you're actually really getting two constants of integration, because one constant of integration is going to be from the term that is in the x direction, and the other is going to be from the term in the y direction. So I'm really going to break this apart in a lot of detail here. So before, what I was doing was I was saying that the integral of the sum is equal to the sum of the integrals. But let's write that very explicitly here. So this integral of the sum that I have here is really a sum of integrals. And I'm going to bring out my I hat to the front, because it's just a constant. You can move constants across integral signs. So this is going to be I hat integral 0 dt plus j hat times the integral of minus beta t dt. And now let's do our integrals here. So the integral of 0 is 0, but we also get a constant of integration here, because whenever you do an indefinite integral, you're going to get a constant integration. So this is going to be I hat times, we'll call this, because we were using a c already, we're going to call this one a c sub 1, okay? Just to denote that it's different than the c that we have in our problem, plus j hat times minus beta t squared over 2 plus another constant of integration, c2 dt, right? And again, the reason why I'm getting multiple constants of integration is because one of these integrals is in the x direction, one of them is in the y direction, or sorry, one of these terms is multiplied by the x hat, or the I hat in this case. One of them is multiplied by the j hat. And so when you do this, you have to be very careful and you make sure that you're getting the appropriate number of constants of integration. Okay, so now this is our velocity vector as a function of time. And as always, when we're doing these, we need to evaluate for our constants of integration. And so when we do this, we're going to say that v of t is equal to 0 is really just this velocity vector v1, right? So we can say this is equal to v1 vector. But this is, as is, incompatible with the way that we've written our velocity vector, because our velocity vector is written in terms of components. And so what we need to do is we need to use this initial condition to write it in components. And so if we have this velocity vector here that is, let's slide this over so that I'm on the screen here. So here's our initial velocity vector, right? It looks like this. And I'm just going to take this as a magnitude, okay? Now, this has components, right? It has a component in x, it has a component in y, angle theta. Now this is just our trig, right? So we're going to say that along the x direction, because this is the adjacent side of the triangle, this is going to be v1 times cosine of theta. And along the y direction, because this is opposite, this is going to be v1 sine of theta, okay? Now, I had mentioned this before, but I'm using some notation here, so I think it's worth mentioning again. When I'm writing v1, this is shorthand. This is shorthand for the magnitude of v1 vector, okay? So when I'm writing this v1, that's really what I mean. It's just the length of the v1 vector. It's the magnitude of v1, okay? So this now can be written as v1 cosine of theta I hat plus v1 sine of theta times j hat, okay? Now, if we evaluate our function v vector of t at t is equal to 0, that's what we have here. And by doing that, we can find what c1 and c2 are. So c1 is a little bit more straightforward because that's just going to be constant always. So c1 is equal to v1 cosine of theta. And evaluating the second term here at t is equal to 0 says that this is going to be minus beta 0 squared over 2 plus c2 is equal to v1 sine of theta. And then this term is 0. I'm evaluating it at 0. And so that says that c2 is going to be v1 sine of theta. So our velocity vector, v vector of t, is going to be equal to v1 cosine of theta I hat plus, I'm going to put a parenthesis here, minus beta t squared over 2 plus v1 sine of theta times j hat. Okay, so let's put a box around this because this is our velocity vector written in terms of all the things that we know. Okay, now the last part that we need to do for this is we need to determine what our position vector is. So to determine our position vector, same process we've gone through plenty of times. We say that the velocity vector, v vector of t, is equal to dr dt. Multiply both sides by dt, and we integrate. So that says that r vector as a function of time is going to be equal to, r vector as a function of time is going to be equal to the integral of v vector as a function of time dt is equal to the integral v1 cosine of theta I hat plus parenthesis minus beta t squared over 2 plus v1 sine of theta times j hat. Let's put a big bracket out here, multiplied by our dt. Okay, so integral of the sum is equal to the sum of the integrals. This is really equal to the integral of v1, and let's bring our I hat outside, v1 cosine of theta dt plus j hat integral parenthesis minus beta t squared over 2 plus v1 sine theta dt. Let's do the integral, or do the integrals that we have here. So this is going to be equal to v1 t cosine of theta plus a new constant of integration, we'll call it c3, times I hat plus minus beta t cubed over 6 plus v1 t times sine of theta plus c4, explosive value there, times j hat. Okay, so now the last thing that we need to do to get our position vector as a function of time is to say we have some conditions for this. We know that v of t is equal to 0 coming from our diagram here, all right? Coming from our diagram here. This starts at the point 0, comma a. So that says that when I evaluate this function, r of t is equal to 0, this is going to be equal to 0 I hat plus a times j hat. So let's evaluate the function that we have in this line above here. So r vector of t is equal to this, and then use these conditions to solve for C1 or C3 and C4. And so that says that v1 times 0 times cosine of theta is equal to, plus cosine of theta plus C3 is equal to 0. This says that because this term right here is itself 0, this says that C3, this implies that C3 is equal to 0. And the last one, this is going to be minus beta 0 cubed over 6 plus v1 times 0 times sine of theta plus c4. Again, this goes to 0, this goes to 0. C4 is going to be equal to a. Okay, so C4, this implies C4 is equal to a. And now we can write our position vector. R vector as a function of time is going to be equal to v1t cosine of theta times I hat plus negative beta t cubed over 6 plus v1 t sine of theta plus a times j hat. Okay, and this is our position vector. Okay, so we've managed to find our velocity vector and our position vector. Okay, so we'll move on to the next portion of this question in just a second once I move things around. Okay, so the last part of this question is, now that we have our position vector as a function of time, we want to find what the magnitude of the robot's initial velocity must be if it leaves the initial point at a known angle theta as shown. And what it's trying to do is it's trying to get to this point C, comma D. Okay? So what this means This one's pretty quick, actually. All we want to do is we want to say that there is some special time when we evaluate this position function that I'm going to call t star. So at this special time, the robot's position is just going to be the position c I hat, and I'm going to move this over, so I mean, it might look a little funny right now, but you'll see why I'm doing this in a second, times d j hat. Okay. So now what this means is we're going to take this function that we have above this line, and we're going to take the x term, evaluate it at t star, take the y term, evaluate it at t star, and then the x term is going to be equal to c when evaluated at t star. The y term is going to be equal to d evaluated t star. Now if we look at this plot, we can kind of draw what's going to happen here. This robot's going to kind of do something like that maybe. And then we can think about all the times that it's spent along this path. And at this very special time, this is going to be t is equal to t star. A very special time is when it's actually at CD. That's what this equation is telling us ultimately. Okay, so when we do this, what this says is we're going to have some c is equal to v1 t star times cosine of theta, and d is going to be equal to minus beta t cubed over 6, and remember this is a t star, t cubed, plus v1 t star times sine of theta plus a. Okay. Now, in order to find what v1 is, we have two unknowns, two equations here. So we don't know what v1 is, and we also don't know what t star is. So in order to find v1, what we're going to have to do is we're going to have to eliminate t star from the equations. And so in order to do that, you can take one equation, solve it for t star, and then plug it into the other equation. So what I'm going to do is I'm going to take the first equation right here, and I'm going to take this and I'm going to solve for t star. When I solve this equation for t star, I see that t star is going to be equal to c divided by v1 times cosine of theta. Okay. So now that I've done this, what I can do is I can take this t star that's expressed in terms of other quantities, other variables or values that we're looking for or we know, and take this and plug it into the other equation. So when I do that, I'm going to get something that looks like this. So d is going to be equal to minus beta over 6 times c, sorry, that's a phi, so this is going to be a c divided by v1 times cosine of theta. This is going to be cubed plus v1 times c over v1 cosine of theta times sine of theta plus a. Okay. Now, what we want to do from this equation is just solve for v1. Now, when you look at this, maybe easier said than done, but something to notice here is that this v1 and this v1 are going to cancel. Okay. So that's going to allow us to move everything else to the other side. So I'm actually going to move this beta over here to this side, move this d over here to that side, so I have everything positive ultimately. So what this is going to say, is that beta over 6 times c over v1 cosine of theta cubed is going to be equal to c times sine over cosine is just tangent, so this is going to be c tangent of theta plus a minus d. Okay. Now, in order to find what v1 is, we're going to still have to do a little bit more here to get everything together. So we have to multiply both sides by 6 over beta. So get rid of this beta prefactor. So when we do that, we have c over v1 cos theta cubed is equal to 6 over beta times c times tangent of theta plus A minus D. Okay? Now, the next thing that we can do to get rid of this cube is to take the cube root of both sides. So both sides of the equation, 1/3 power, gone. So this is going to be C over V1 cosine of theta is equal to 6 over beta C tangent of theta plus A minus D, and the whole thing to the 1/3 power. Now we're almost there. Now what we need to do is we need to move this C and this cosine of theta to the other side. And so this says that 1 over V1. So we're going to multiply both sides of the equation by cosine of theta over C to cancel it from on the left side. So we're going to move this over to the right. This is going to be equal to cosine of theta divided by C times 6 over beta times C tan theta plus A minus D to the 1/3 power. Now the last thing that we need to do is we need to flip the whole thing over because our V1's in the denominator. So really this is the same thing as V1 to the minus 1. So we can take the whole thing to the minus 1. Okay. So when we do that, we have V1 is going to be equal to cosine theta over C to the negative 1 is going to give us a C over cosine of theta. The rest of it, somehow I lost this should be, yeah, this is fine. This is fine. This term right here, I'm just going to put, instead of 1/3, just make it minus 1/3. So this is going to be 6 over beta times C tan theta plus A minus D, and then the whole thing to the minus 1/3 power. Okay, and this is our answer. Okay, now, just as we usually do, let's make sure that dimensional analysis works out. This one was kind of complicated, so we need to make sure that the units work out. So in order to do this, we need to go all the way back to our first equation here and figure out what the units of beta are. So beta times t is going to be units of acceleration. So beta is going to have units of meters per second cubed. Okay. If you don't see that, go through the algebra, make sure that you believe that. But this is going to have units of meters per second cubed. So beta has units of meters per second cubed. C, A, and D all have units of meters. So if I'm going to look at this whole thing, if I want to know what the units of the left side are, I can write this as, this is going to be units of meters. This is going to be units of meters per second cubed. And there's a 6 there, don't care about it, but I'm going to put that in the denominator, times units of meters, because everything in this portion right here has units of meters. And then let's raise the whole thing to the minus 1/3. Okay, so when we do that, we're going to see that our meters are going to cancel. This is going to be, this 1 over seconds cubed in the denominator is really going to be a seconds cubed in the numerator, but this is the minus 1/3. We have meters. This is going to be equal to meters. When we raise it to the 1/3 power, this is going to be seconds, and then it's to the minus 1, so this is going to be in the denominator. So our units are going to check out here. So barring any problems that I might have had with, maybe this wasn't actually a 6, maybe it was like a 5, barring any problems like that, this answer is correct dimensionally. Okay, so that's going to be it for this one. I hope you guys enjoy, and good luck studying.